So these are law of conservation of energy. Total momentum before equals the total momentum after. Total momentum can't change. So you add up the momentums of all the things before and set those equal to all the things after and solve for whatever variable you need to solve for. In this case, it's the velocity of this thing afterward. So this is moving, this is still. Here, this collides with that, they stick together, they move together. In the beginning, the momentum of this is mass 4 times velocity 3, so that's going to be 12. And the momentum of this is 2 times 0 because it's not moving. So the total momentum is 12. And in the end, the mass is 6, the velocity is v, so the momentum is 6v. So 6v equals 12, and therefore v equals 12 over 6, or 2, which makes sense, because if you have something big and fast hitting something smaller and motionless, they're going to keep moving, they're going to be a little bit slower than the fast thing, the big thing was before. Here we've got something motionless that has no momentum, and therefore even after it splits apart and pieces of it start moving, the total momentum has to be 0, meaning the positive momentum of this has to be equal and opposite to the negative momentum of that, so they can add up to nothing, just like what they had before. Momentum before is mass times velocity, 0. The momentum of this is 2, that's the mass, times the velocity, -2, so it's -4. And that means the momentum of this has to be positive 4. So the momentum is mass, 1 kilogram times v. If you set all this equal, solve for v, you get 4. Here we've got a big fast thing, or a heavy, massive fast thing, chasing a less massive, slower thing. And they're going to hit and have a speed somewhere in between. So the momentum of that's mass times velocity. Add that to the momentum of this, mass times velocity. And that total momentum should equal total momentum here, which is the total mass times velocity. Now I could, if I wanted to, say the momentum after is 3 kilograms times v plus 2 kilograms times v, since they're together, but it's easier just to do 5 kilograms times v. This is the second time I've done this video. The first time I couldn't figure out what the heck Mr. Chase had done here, but got it. It's all straightened out now. And I think for these other problems, as I give you some suggestions about how to solve them, I don't even know if I'm going to suggest that you do it the way Mr. Chase did it. Maybe I'll just suggest a different thing. So here's the deal. In this is the problem that confuses students. So we've got a child in a boat, the boat's motionless, the child's motionless, and the child has a package, which is 6.4 kilograms, and the child is 26 kilograms, the boat's 45 kilograms. They're all motionless in the beginning. Then the child throws the package, which flies to the right, must be to the right because this is positive, 10 meters per second. So now this has momentum to the right, which means this has got to have momentum to the left, because the total momentum has to be the same as the momentum here, which was 0. So here's the way Mr. Chase wrote out the law of conservation of momentum here. This is the beginning. This is it. And he's saying let A represent the boat and the child together. So A is this mass, which is 26 plus 45. And let B represent the package, which is 6.4 kilograms. So in the beginning, the total momentum is the total mass, the mass of everything, times the velocity. It would be nice if we just stuck in a big 0 for this, because there's no velocity. This all amounts to 0. That kind of confused me as I was going from this step to this step. So then in the after, now we've got the package, which is represented by B. It's got a positive velocity, and then the person in the boat, represented by A, they're going to have a negative velocity. So this is the momentum of the boat and the person. It's the total mass times their velocity plus the momentum of the package, which is its mass times velocity. Now this makes sense if you keep in mind that total momentum before is 0. So ma v prime a plus mb v prime b equals 0. So you can subtract mb v prime b from both sides and then divide both sides by ma, and you get this, and you can plug everything in there and solve. Or you can just plug everything in to begin with. So this mass would be 26 plus 45, and this is 6.4, and this is whatever 26 plus 45 is again, and this is what we're solving for, and this is 6.4, and this is 10. All right. Railroad car travels alone on level frictionless track. A 5,350 kilogram load initially at rest is dropped into the car. What will be the new car's speed? So basically, here's a railroad car, and it's got a velocity of 18 meters per second, and essentially it's colliding with this load, which I'll just draw the load here. Velocity equals 0 meters per second, and the mass is 5,350, and the mass of this is 12,600. So if you wanted to, and then they're going to move together, so if you wanted to set this up in a way that doesn't look like that, you could just say the momentum before equals the this mass times its velocity plus the momentum of this thing, which is going to be 0, times its velocity. That's the total momentum before, and that equals the total momentum after. Now after, these two masses are going to be the same, so we're going to have 1260 or 12,600 plus 5,350, that's the mass, times v, and that's what we're solving for. So very doable. Number 12, this is an interesting one. 3,800 kilogram open railroad car coasts along level tracks with a speed of 8.6 meters per second. So this sounds kind of the same as the other one so far. So this is 3,800 kilograms. That's the mass. And then we've got the velocity, 8.6 meters per second. So we can figure out the momentum from that. Snow begins to fall vertically and fills the, I think it means fills the car at a rate of 3.5 kilograms per minute. What's the speed of the car after 90 minutes? Well, I don't really know why we had to add that complication to it, but this is the number of kilograms per minute. This is the number of minutes. So basically, a mass of snow equal to 90 minutes times 350 kilograms per minute. Whatever that is, this is the mass of snow that is going to fall in this. So it's just like this. It's just like this load being added on. And this will be the mass of the load and its initial velocity, at least in the x dimension, which is what's important here, is 0. I mean, it's falling straight down, but that's not going to speed it up or slow it down in this x dimension. So this is just like the problem before, except that you have to calculate the mass of the snow, and that's